Okay. So look, how much circumference we have here? If the radius is a, the circumference is 2 pi a. Okay, circumference is 2 pi a, and this is the circumference c. Okay, uh, the total surface area of inner conductor is equal to uh, suppose A, which equals to circumference multiplied by the length of the conductor. Is that true? 2 pi 2 pi A dot L. Okay, and say we have Q charges. Q is charge on surface. Okay, so then rho S, surface charge density, is Q divided by 2 pi A dot L, which equals to Q by L equals to 2 pi A, which equals to rho L divided by 2 pi A. This is rho S. Okay, so this is a little bit mathematics, and you are very familiar with this one. Okay, so this is the inner. Okay, so if inner conductor is positively charged, okay, if inner conductor is positively charged, the outer conductor is negatively charged. So rho s of the outer conductor will be equals to minus rho L divided by 2 pi B. B is the radius of the outer conductor. Okay, B is the radius of the outer conductor. Length is the same. So minus Q divided by L divided by, sorry, this no L, divided by 2 pi B. So this is outer conductor. Okay, so here we have these two equations. And that's the case when we have the coaxial cable. Now, can we calculate the electric field of this coaxial cable? Anyone? And we can also calculate, by the way, the voltage also. Okay. So if we use this little bit mathematics, we have already gone through this mathematics. This is the Gauss law, remember? Psi equals to
Yes,
d
sir.
dot ds equals to, yes, exactly, q enclosed by the surface, q enclosed by the surface. So if you put things together, this is d rho, this is surface area 2 pi rho L. Rho is a general value. Rho equals to a for the inner surface, and rho equals to b for the outer surface. Okay, and rho is any value between a and b. Okay, rho is any value between a and b. Okay. Okay, so that's from the Gauss law. We can calculate, we have this equation. Okay, if you manipulate this equation a little, you will calculate the electric field. You'll calculate the electric field, which is from this positive charge towards this negative charge. Every positive will have a negative on the outer. Okay, this electric field is equal to rho L divided by 2 pi epsilon naught, because we have epsilon r here. Okay, epsilon r, epsilon naught, epsilon r rho. This equation, by the way, is already known to us. This is E line charge. Okay, and it's also the
Yes,
equation of
sir.
electric field intensity for the coaxial cable, and we know that if this is positive charge, and the electric field starts from here, this electric field will end on the outer surface. It cannot penetrate the outer surface. It cannot. Why? Why the electric field cannot penetrate the outer surface? Again,
सर
again.
क्योंकि इलेक्ट्रिक फील्ड क्रॉस नहीं कर सकती है एक दूसरे को,
Exactly.
लाइन से।
Yes, this is negative charge. Electric field starts from here, and here there is no electric field outside because the electric field cannot cross metal. Okay, the outer conductor, the outer wire of the coaxial cable is a conductor. So the electric field cannot cross the outer conductor. So it will stay, it will be confined between the inner conductor and the outer conductor. It's not going to cross the outer conductor. Okay, so that's the electric field of the coaxial cable. This is the so we have, wait a second. Okay, see, this is the electric field. This is the electric field of a coaxial cable. Now, can we calculate the voltage of this electric field? Remember, the voltage
यस
is
सर।
E dot dl. dl is the path. Okay, dl is the path. In this case, dl is how, in which direction? In the rho direction. So we have d rho. And electric field is in which direction? E rho. Okay. And if you move from A to B, A is, this point is A, and the outer point is B. If you move from A to B, right? This is the surface of inner conductor, okay? Or say radius of inner conductor, okay? And this one is B is what? Radius of outer conductor, okay? This is basically surface of inner surface, inner surface of outer,
आउटर कंडक्टर।
okay, outer conductor. Yes. And this one is basically the outer surface, outer surface of the inner conductor. Okay. So if I know, I can really calculate the voltage VBA from A to B. I can really calculate the voltage VBA between those 2 points. Okay. So if I calculate the voltage, if I calculate the voltage between the inner wire of the, if I calculate the voltage between the inner wire of the coaxial cable and the outer wire of the coaxial, I can really calculate the capacitance also then. I can then calculate the capacitance also. Okay. And it will be so easy. Okay. So VAB, let me stick to one kind of uh, notation. Okay, VAB. Okay, so VAB is VA minus VB. It will be this equation. Okay, and how we do that? Our VAB is integral from A to B E dot d rho, E rho d rho. So just put the values from A to B. E rho is how much? Rho L divided by 2 pi epsilon naught epsilon r, right? Dot 1 over rho d rho. Is this clear? So knock out some of the constant or bring them outside of the integral. Okay. Okay. बात की समझ आ रही है?
यस सर समझ आ रही है।
If I flip, if I make this B, if I make this A, I have to introduce negative sign here. This already we know. Okay. We know this already. So let me place
Yes, sir.
my original A here and B here, and I will leave this step here, the flipping, this negative sign. Okay. So when we the integral of 1 over rho is integral of 1 over rho from A to B or B to A, whatever the value is, say B to A, is natural log of rho from B to A. Okay. So this is how you can do things. Okay. Okay. So this equation is already known to us. Integral 1 over rho d rho is natural log of rho plus c. But if I know my limit x1 rho 1, if I know the initial value rho 1 and the final value rho 2, I don't have this constant. Remember, this is the magnitude only. Okay, this is always the magnitude. ये हमेशा याद रखिए, ये magnitude ही आना है. यहाँ पे नहीं बताया गया, लेकिन but this one is always the magnitude. Okay, this one is always the magnitude. Okay, so now when you bring this charge on this side, so when you bring the charge on this side and flip the equation, bring charge on the left side and flip the equation, right? So then you can calculate the capacitance. So the capacitance of the coaxial cable is very straightforward. Okay. Later on in chapter 8, we will find the inductance of coaxial cable, that we will find later on. Okay. When we do that, then we will find some very interesting phenomena when we calculate the inductance of the coaxial cable. Okay. So for now, we calculated the, so that means every coaxial cable have capacitance. Okay. What if we fill this conductor, and this one is the inner conductor and the outer conductor? What if we fill the two conductors with epsilon R1, then epsilon R2, then epsilon R3 with three different dielectrics? So it's same like we have three capacitors between two coaxial cable. Very similar case as we discussed here. Here, very similar thing. That was flat structure. Coaxial cable is a round structure. Okay, it's a round structure. So if you fill the coaxial cable with three different dielectrics, you will end up on three different capacitances. And if the filling is in this fashion along the circumference, then the three capacitors are in series. Okay. What if you fill the coaxial cable with this sort of arrangement? Say here is epsilon R1 and here is epsilon R2. This means that we have two capacitances again inside the coaxial cable, but both capacitors look like in parallel.
Parallel.
Okay. So this was
Yes, sir. Clear.
this kind of thing. But with coaxial cable, you never do this. Okay. You never put coaxial cable in this fashion. You will never find a coaxial cable having dielectrics slotted in this way. But this may occur as a problem because of the oxidation of the coaxial cable. This sort of thing may occur, and it's a problem. Okay, and that will change the capacitance of the coaxial cable. And once the capacitance of the coaxial cable changes, some serious things will occur. Some serious bad things will occur. If the capacitance of the coaxial cable will change, some seriously bad things will occur, and those effects, those bad effects, we will discuss when we discuss the inductance of the coaxial cable. We will combine these two together later on, and we'll find some interesting phenomena. Okay, so this also means this coaxial cable for us is very important because it's everywhere in telecom. It's everywhere. Okay. What about this structure? Anyone?
सर इसमें पैरेलल में भी हैं कैपेसिटर्स और सीरीज में भी हैं, कॉम्बिनेशन हो
हाँ,
गया उसका.
हाँ, exactly. But this will never occur. This will never give you parallel combination or series combination. It will always give you a very disturbed capacitance. You will never be able to calculate the capacitance of this structure precisely. It will be continuously changing. Why it will continuously change? Because there is by the uh, by by boundary conditions, this suppose et1 shall be equals to at the boundary et0 and shall be same as this value et2. Okay, but the problem is here again the normal component will change. So here the in the pink we have et2, here we will have et3. So see, it's really become a normal component, and this will never be same as this one and will never be same as this one. So it will always produce a very disturbed pattern for the electric field. The electric field will never stay the straight line. Okay, that's a bit that's a little problem, and this structure will never give you a capacitance, a defined capacitance. It will never give you. Okay, any question here?
ओके सर. सर इसमें इसका मतलब ये भी होगा कि हम जब भी इस कैपेसिटर को मतलब चार्ज करेंगे तो ये डिफरेंट कैपेसिटेंस दे सकता है.
हाँ, और ये बेसिकली बाउंड्री कंडीशंस को वेरीफाई नहीं कर पा रहा. ठीक है,
ओके सर, क्लियर है.
राइट. So we went through the capacitance. Uh, Based on that concept, we have just like with the coaxial cable. See, this was the coaxial cable, right? This was a better coaxial cable. Look, if I slice this coaxial cable like this way, okay. When I slice the coaxial cable, uh, this way. When we slice the coaxial cable right from the center, this way, and say we make it flat, okay, we make it flat. See, we will end up on this kind of structure if you open up, okay. We will have this green outer conductor, okay. This is this green outer conductor, and this pink inner conductor is here, and there was a dielectric epsilon r, so that same dielectric epsilon r is here. So if you open up the coaxial cable, slice it, open it up, make it flat, you will end up on a new structure called a strip line. Strip line is again a transmission line used for communication. But strip line, a coaxial cable, coaxial cable is a kind of transmission line you use for say 10 meters, say 100 meters, say 1 kilometers for long distance. Strip line, on the other hand, these days used for inter-component communication on a transmitter or on a receiver. So it's inside the board. It is fabricated on the board. You may fabricate them on your mobile phone circuit boards to have a communication between two different components on a mobile circuit board. So they are very small. They're used for very small distance. But the behavior is very refined behavior. Uh, Probably the best of all transmission lines, the metallic transmission lines. The best transmission line, by the way, is a fiber optic cable, but that's not a metallic. That's purely a dielectric material. There's no metal in the fiber, and used for very long distance, like hundreds of kilometers. Strip lines is used for very short distance, very short distance. Uh, if you if you slice this further, if you slice this further, right? If you slice this further and reject the upper part and just throw the upper part, just reject the upper part, okay? If you simply throw the upper part, you will left with this sort of structure, okay? You're left with this lower structure. This structure is called as microstrip. Very easy to fabricate. Typically, you etch the PCB of very high frequency to end up on a microstrip line. Microstrips are used again for inter-component communication on the transmitter or on the receiver. So ये भी माइक्रोस्ट्रिप आजकल बहुत पॉपुलर है. बेसिकली पीसीबी हाई फ्रिक्वेंसी पीसीबी की एचिंग से ही बनते हैं. आप सिर्फ लाइनें बनाते हो. See, say we have, uh, say we have this metal, right? Upon this metal, say we have this sort of dielectric. Okay, this sort of dielectric. Okay, this sort of dielectric. Let my dielectric is little bit green. ठीक है. और इसके नीचे अगेन से मेरे पास कॉपर है. So I have this copper below it. पीसीबी है ना, पीसीबी. तो पीसीबी में ये कंडक्टर है. ओके, फिर डाइलेक्ट्रिक है, फिर ऊपर एक और लेयर है कंडक्टर की. दिस अपर लेयर कंडक्टर. ठीक है, ये भी कंडक्टर है. सो ये पीसीबी बन गया ना. हाई फ्रीक्वेंसी पीसीबी अगर है तो हम ऊपर लेयर से काफी मेटल उतार के, काफी मेटल एच करके सिर्फ ट्रेसेस रहने देते हैं, रास्ते रहने देते हैं, ताकि दो कंपोनेंट को हम ज्वाइन कर सके. एक कंपोनेंट इस एंड पे पड़ा होगा, दूसरा कंपोनेंट इस एंड पे पड़ा होगा. तो ये जो ट्रेसेस हम ऊपर वाले कंडक्टर बाकी एच करके निकालते हैं, सिर्फ रास्ता छोड़ देते हैं, ये हमारे पास माइक्रोस्ट्रिप ट्रांसमिशन लाइन बन गई है. Okay, so we have a ground plane, we have a dielectric, and then we have the upper ground plane. Okay, so we end up on a microstrip transmission line. Again, this has capacitance. This has capacitance, of course. Why? Because this is metal. This one is dielectric. This is again metal. So we have capacitance here between these two. Okay. So for any communication or transmission line, capacitance is the key parameter to design that transmission line. And we'll explore its importance, okay, when we also find its capacity inductance. Any question here? No question? I guess it's enough for the day. Okay,